Now let's look at a problem dealing with systems of equations. Determine whether -4, 3 is a solution of the system. Our first equation is x plus 2y equals 2. Our second equation is x minus 2y equals 6. To be a solution to the system would mean that we can take this point and substitute x equals -4 and y equals 3 into both equations, and in each case come up with a true statement. So let's try that now. We'll have in our first case, let's take x plus 2y equals 2. That would be -4 plus 2 times 3. We're trying to see whether or not we're going to come up with 2. Well, that would be -4 plus 6. And -4 plus 6 does indeed equal 2. So it does fit the first equation. Let's try the second equation. X minus 2y equals 6. We'll substitute for x, that's -4, minus 2 times our y value of 3, and we're trying to see whether or not we'll get 6 as a result. -4, we'll have -2 times 3, we'll write it as -6. -4 minus 6 is -10, and we can see that that does not equal 6. To be a solution, remember, means it has to satisfy both equations, so we would have to say no, -4, 3 is not a solution. Let's look at another example involving linear systems. In this case, we want to solve the system by graphing. We have two straight lines. 2x plus 3y equals 6 is the first. 2x plus y equals -2 is the second. We're going to begin by graphing the equation 2x plus 3y equals 6. And we can accomplish this by using our intercept method. Let's let x equal 0 in the equation and solve for y. Now, this becomes pretty easy if you recognize that when you substitute in 0, you're going to take 2 times 0, and it's going to be eliminated from the equation since it's equal to 0. So usually when I'm doing this, I'm just covering up one of the terms because the format of the equation makes it easy to do. So we're going to end up now solving the equation 3 times y equals 6, and we come up with a value of 2. If we find our other intercept, we're letting y equal 0. That's going to give us 3 times y, which is 3 times 0 is 0. And now we're solving the equation 2x equals 6, in which case x has to equal 3. Let's graph that equation now. We're going to plot the points 0, 2, and 3, 0. And we're going to connect the dots in order to graph our first line. Okay, let's do it pretty accurately. Now, let's move to the second line. We have the equation 2x plus y equals -2. If we let x equal 0 in the equation, then this term is eliminated and we have y equals -2. If we let y equal 0 in the equation, then we're solving the equation 2x equals -2, and our x value would have to equal -1. And let's plot that equation now. Using the green pen, we're going to have 0, -2, and -1, 0, and we'll connect the dots. Now, the solution to the system is going to occur where the two lines are going to intersect, because that would be the point which lies on both lines and therefore satisfies both equations. So let's see what the coordinates of this point would end up being. We move 1, 2, 3 units to the left, telling us that the x value is -3, and then we move 1, 2, 3, 4 units up, telling our y value as +4. We can double check by substituting these values into the equation. Let's do that mentally. We have 2 times -3, which would be -6, plus 3 times 4 is 12. -6 plus 12 does equal 6. Let's try it in the second equation. 2 times -3 is -6, plus 4 is going to be -6 plus 4, which is equal to -2. So we can verify that this is the solution by substitution into both equations. Now let's look at solving a linear system by a more algebraic method. Solve by the substitution method. We have the equation y equals 3x minus 7. Second equation, 5x minus 2y equals 8. Step 1. Solve either equation for one variable in terms of the other. Well, if we notice, our first equation is already solved for y, so we're going to use that. Y equals 3x minus 7. Step 2. Substitute the expression from step 1 into the other equation. Notice that in step 1 our equation solved for y. So we take our second equation, and where we see the variable y, we're going to replace it with 3x minus 7. Notice that what occurs then is we end up with a single equation with one variable, as opposed to having two equations and two variables. Now we're going to take that resulting equation, which it contains one variable, and we're going to solve it. So once again, what we had was 5x minus 2 times 3x minus 7 equals 8. Let's use the distributive law in order to simplify. 5x, we're going to have a subtraction of 2 times 3x, that's going to be a negative 6x. We're going to have a subtraction of 2 times negative 7, that's going to be an addition of 14, and that equals 8. Continuing on, we can combine 5x minus 6x to give us negative x. Then we're going to have plus 14 equals 8. Let's subtract 14 from both sides of the equation. Negative x is going to equal 8 minus 14, which is negative 6. And finally, divide both sides of the equation by negative 1 to give us x equals 6. Step 4, back substitute the obtained value into the equation from step 1. Well, in step 1, let's recall that we had y equals 3x minus 7. We're now going to take our value of x and substitute into this. We're going to have 3 multiplied times 6 minus 7. Our y value is going to equal 18 minus 7, and so our y value is equal to 11. The last step is to check the proposed solution in both of the system's given equations. So just to rewrite quickly, we had an equation y equals 3x minus 7, and we had the equation 5x minus 2y equals 8. We're going to take our proposed solution, which has our x value of 6 and our y value of 11, and substitute into each equation. To begin with, then, we'll have 11 equals 3 times 6 minus 7. So 11 is supposed to equal 18 minus 7, and of course it does. And in our second equation, we're going to have 5 times 6 minus 2 times 11, and we want to see whether that equals 8. 30 minus 22 indeed does equal 8. So we've verified our solution as the point 6, 11. Here's another example of working with a linear system. Solve by the substitution method. 3x plus 2y equals negative 1. X minus y equals 3. Step 1 is to solve for one of the variables in one of the equations. When we become pretty proficient at this, we're going to try to pick out the most efficient method for doing it. If we try to solve for the x in the first equation, we're going to have to, at one point, divide by 3, giving us a fractional value. If we decide to solve for y in the first equation, we'll have to divide by 2, again, giving us a fraction. If we decide to solve for x in the second equation, we can do it in one step. Notice if we try to solve for y, we'd have to divide by negative 1 at some point. The easiest variable to solve for is going to be x in the second equation. We can accomplish that in one step. X is going to equal y plus 3. Now we're going to take that value and substitute into the other equation. So where we see x, that is, multiplied by 3, we're going to replace it with y plus 3. So we'll have 3 times y plus 3 plus 2y equals negative 1. Now let's use the distributive property of multiplication over addition. 3 times y is 3y, plus 3 times 3 is 9. We'll rewrite the rest of the equation. Combine like terms. 5y plus 9 equals negative 1. Let's subtract 9 from both sides of the equation. 5y equals negative 10, and divide by 5 to give us y equals negative 2. Now recall that we're going to back substitute in order to solve for the other variable. That means we're going to take our value of x equal to y plus 3 and substitute in the value of y that we've just found. We end up with negative 2 plus 3, giving us our x value equal to 1. So our proposed solution has coordinates 1, negative 2. We can easily check this by substituting into our given equations. We'd have 3 times 1 plus 2 times negative 2. Let's go ahead and just evaluate that. We end up with 3 minus 4, which is equal to negative 1, and that checks with our first equation. And in our second equation, we would have 1 minus a negative 2. We can evaluate that as 1 plus 2, and that equals 3, and that checks also. So our solution to this system is the point 1 comma negative 2. Here's now another method for solving linear systems. Solve by the addition method. Our equations are 4x plus 5y equals 3 and 2x minus 3y equals 7. Step 1. Rewrite both equations in the form a times x plus b times y equals c. Well, we don't have to do step 1 because it's already in the format that we need. Let's move on to step 2. If necessary, multiply either equation or both equations by appropriate numbers so that the sum of the x-coordinates or the sum of the y-coordinates is 0. We can see that right now if we attempted to add these equations together, we would not end up with the sum of the x-coordinates equal to 0, nor would we end up with the sum of the y-coordinates equal to 0. However, if we do a little bit of manipulation, we can make that happen. Let's just look at our x-coordinates. We have 4x in our first equation, and we have negative 2x in our, we have positive 2x in our second equation. I was anticipating my next step. I'm going to multiply the second equation by negative 2 in order to accomplish what's being requested here. So that is, I'm going to take my first equation and leave it as is, 4x plus 5y equals 3. In my second equation, I notice that if I multiply by negative 2 on both sides of the equation, then I can rewrite this as negative 4x. We're going to have plus 6y equals negative 14. Now notice then that the sum of the x-coordinates in this case would equal 0. Let's move now to step 3. We want to add the equations. I'll quickly write it down again. We had 4x plus 5y equals 3 and negative 4x plus 6y equals negative 14. Adding together, our x's are eliminated. We're left with 11 times y equals, and adding here gives us a negative 11. We're now able to solve for y by dividing both sides of the equation by negative 1. Now, we've been able to add and solve the equation, and now we want to think about finding the other value. So, went ahead and did that step, solve the equation. We come up with y equals negative 1. Now we're going to go to back substitute to find the value of the other variable. For instance, we had the equation 4x plus 5y equals 3. We've now found y equals negative 1. Let's back substitute. We'll have 4 times x plus 5 times negative 1 equals 3. Let's solve this. We're going to have 4 times x minus 5 equals 3. Let's add 5 to both sides of the equation. 4x equals 8, and then x is going to equal 2. So we have a proposed solution of 2 comma negative 1. We need to check this solution. Quickly, going back to the original, we had 4x plus 5y equals 3, and we had 2x minus 3y equals 7. We want to make sure we go back to the original format so that if we've made any mistakes, we'll catch it. So don't go back to one of the equations where you have changed it in any format. We're going to take, in our first case, 4 times 2 plus 5 times negative 1, and let's evaluate that. We would have 8 minus 5, and that does equal 3. In our second equation, we would have 2 times 2 minus 3 times negative 1. Let's evaluate this. We're going to have 4 plus 3, as we multiply, we have a subtraction of negative 3, which is plus 3, and that's going to give us 7, and that also works. So our solution of 2 comma negative 1 is correct. Here's another example using the addition method for solving linear systems. Solve by the addition method. First equation, 3x equals 2 minus 4y. Second equation, 5y equals negative 1 minus 2x. Our first step is to rewrite each equation in the format where we have a number times x plus a number times y equals a number. Our first equation, we can add 4y to both sides of the equation to get that format. We'll have 3x plus 4y equals 2. In our second equation, we can add 2x to both sides of the equation to get that format. We'll write the 2x in the front plus 5y equals negative 1. To use the addition method requires us to figure out a way to add the two equations together so that either we end up getting 0 in our column for x's or 0 in our column for y's. Let's work this one by trying to end up eliminating our y values. I notice that I have a 4y in my first equation, a 5y in my second. If I multiply my first equation by positive 5, go ahead and indicate that here. I'll multiply by 5. And if I multiply my second equation by negative 4, then we'll be able to have coefficients that will have opposite signs, and they'll add together to give us 0. Let's do that now. We'll have 5 times 3x, which is going to be 15x, plus 5 times 4y, which is going to be 20y, equals 5 times 2, which is 10. In our second equation, negative 4 times 2x is going to be negative 8x. Negative 4 times 5y is a subtraction of 20y. And negative 4 times negative 1 is positive 4. Let's add. 15x minus 8x is 7x. 20y minus 20y is eliminated as needed. 10 plus 4 is 14. And now we divide by 7 to give us x equals 2. We now back substitute to find a value for y. So, for instance, in our second equation, we have 5y equals negative 1 minus 2 times our value of x, which I'm going to write down, go ahead and substitute in as 2. 5y is going to equal negative 1 minus 4. 5y equals negative 5, and y equals negative 1. Our proposed solution is 2, negative 1. We need to double check this. Now, we'll substitute into our first equation to see what happens. We'll end up having 3 times 2. We want to see whether that's going to be equal to 2 minus 4 times negative 1. On the left-hand side, we end up with 6. On the right-hand side, 2 minus a negative 4 would also equal 6. So it does check in the first equation. Let's just try it in the second one. We're going to have 5 times negative 1. We want to see whether that equals negative 1 minus 2 times 2. 5 times negative 1 is negative 5. And on the right-hand side, negative 1 minus 2 times 2, which would be negative 1 minus 4, is also equal to negative 5. So it does check. Our solution to the system is the point 2 comma negative 1. Here's another system to solve. The system is the equation x plus 2y equals 4. Second equation, 3x plus 6y equals 13. We're going to notice that it's set up in a format which would lend itself to the addition system. So we're going to multiply the first equation by negative 3 in order to get the x values to be eliminated. So I'm going to multiply negative 3 times the left-hand side and negative 3 times the right-hand side. Let's do that. We'll have negative 3x minus 6y equals negative 12. Our second equation we can leave as is. Now let's add. Negative 3x plus 3x is 0. Negative 6y plus 6y is 0. We end up eliminating both sets of variables. We come up with, on the right-hand side, negative 12 plus 13 is 1. Now we know that 0 does not equal 1. Since this is not true, what that leads us to believe is that there is no solution to the given system. In fact, if we went back to graphing here, we'd find out that these two equations are actually going to be parallel to each other with no intersection. Here's another linear system to consider. The system is y equals 4x minus 4 as our first equation, 8x minus 2y equals 8 as our second. The format of the system lends itself to substitution. So we already have our first equation solved for y. Let's take that and substitute into the second equation. That will now read 8 times x minus 2, and instead of putting in the y, we'll put in our 4x minus 4, and that equals 8. Let's simplify by using the distributive law. We'll have 8x minus 8x plus 8 equals 8. We subtract out our x values on the left, leaving us with 8 equals 8. Now, 8 equals 8 is always true. What that indicates to us is that these two equations are always going to be intersecting. And in fact, if we go back to the graphing, what we'd find out is we actually have the same line. What we would say for the solution is that any values, x comma y, that satisfy the first line would also satisfy the second. So any xy that would satisfy y equals 4x minus 4 will also satisfy would also satisfy 8x minus 2y equals 8. Now let's look at an application from business. A company that manufactures running shoes has a fixed cost of $300,000. Additionally, it costs $30 to produce each pair of shoes. They are sold at $80 per pair. Part A, write the cost function, C, of producing X pairs of running shoes. Well, we have two bits of information dealing with how much it costs. We know there's a fixed cost of $300,000, so part of our cost function has to include that. We also have a cost of $30 per pair. Now, we are told that X is going to stand for the number of pairs of running shoes that are produced. So we're going to add to this 30X, and that gives us our cost function. Write the revenue function R from the sale of X pairs of running shoes. Our revenue function deals with how much revenue we take in, or how much we end up making off of each pair of shoes in this case. So we're going to see that they're sold at $80 per pair, which means our revenue is going to equal $80, or 80 times the number of pairs that we sell. Determine the break-even point and describe what this means. Our break-even point will be where our cost is equal to our revenue. So in this situation, we're going to have 300,000 plus 30x equals 80x. We can solve this by subtracting 30x from both sides of the equation. That gives us 300,000 equals 50x, and then dividing both sides of the equation by 50 gives us a value for x of 6,000. Now, what this means is that we have to sell 6,000 pairs of running shoes in order for our cost to be offset by our revenue. Or in other words, at that point, we end up having a profit of 0.